Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 8, Lesson 2 on vertically stretching and compressing functions. In our last lesson, we reviewed how to shift a function left, right, up, and down. And when we shift a function, the fundamental shape of the function does not change. Simply its location changes. Today, we'll start to actually change the shape of the function. So let's get into it. Vertical stretching and compressing. We've now reviewed how to shift or translate a function. In this lesson, we will see how to stretch or compress a function relative to the x-axis. So let's begin and take a look at exercise number 1. Now, in this exercise, you are most certainly going to want to have a graphing calculator, all right? You're going to want to have it ready and open and all of that, and we'll eventually be getting our graphing calculator out as well. Anyway, let's go ahead with exercise number 1. A quadratic function f of x is defined by f of x equals x squared minus 2x minus 8 and is shown graphed below. Two additional functions are defined by g of x equals 2 times f of x and h of x equals 1/2 times f of x. Letter A. Determine formulas for g of x and h of x in terms of x. All right, well this is actually relatively simple, right? Because the formula for g of x should be just twice the formula for f of x, and the formula for h of x should be 1/2 times the formula for f of x. So pause the video right now and see if you can determine formulas for g of x and h of x. All right, let's do it. So g of x is going to be 2 times f of x, which is 2 times x squared minus 2x minus 8, which is 2x squared minus 4x minus 16. Excellent. Let's take a look. F of x, or not f of x, sorry, but h of x is 1/2 times f of x, which is 1/2 times x squared minus 2x minus 8, which is 1/2 x squared minus x minus 4. All right, simple enough, right? That's no big sweat. All right, letter B. Graph both functions on the axes provided and label with their equations. Now, I probably should have pointed this out. What I really want you to do is I want you to take your graphing calculator out. I definitely want you to put f of x in. You want to have this thing sort of as its base right there for you, right? Then what I want you to do is put g of x in as your second equation and h of x in as your third equation. And you could certainly use 0.5 here instead of the fraction 1/2 if you wanted to. Sketch each one of them, right? And try to do your best job on the sketches. They don't have to be perfect in any way, but see what you can do. All right, so of course for me, I've got just the magic of the board, right? So when I have these things, right, f of x was our original curve in blue, g of x is our 2 times f of x in red, and h of x is going to be our 1/2 times f of x in black there. All right, now let's take a look at letter C. Using your calculator's minimum command, determine each function's minimum values. All right, well, we've already taken a look at how to use the minimum command and the maximum command to find the values of turning points. So, or not the values of turning points, but the location of turning points. So pause the video right now and see if you can figure out what the minimum values are for each of these functions. Our original function, our g of x, which was 2 times f of x, and our h of x. Pause the video now and go ahead and do that. All right, well, what we find is that f minimum, right, our original graph right here, that thing had a minimum value at -9. G, which was our graph in red, had a minimum value of -18. And H, a little bit uglier here, H had a minimum value of -4.5. Now, let's just state the obvious right now as we're looking at this, right? G of x was f of x times 2. And notice, right, the minimum value of f was 9 units below the x-axis, when we multiplied it all by 2, it got to be 18 units below the x-axis, and when we multiplied it by 1/2, it was then 1/2 of 9 units, or 4.5 units below the x-axis. Now notice, it was only the y value, though, that actually changed. We started here, and when we multiplied the entire function by 2, that became twice as far from the x-axis. And when we multiplied by 1/2, it became 1/2 as far from the x-axis. And that should make all the sense in the world, because literally, all of this says is that all y values on G will be 2 times the y values on F, and all y values on H will be 1/2 times the y values on F. That's it. Now, kind of important, letter D. What points on f of x did not change when it was multiplied by the factors of 2 and 1/2? Why? So it should be very obvious when I look at this graph that there were 2 points on f of x that stayed the same on g of x, and they stayed the same on h of x. Where are they, and why did they not go anywhere? Pause the video now and think about this for a moment. Well, it's pretty easy because basically you're just looking for intersection points, right? And these 2 points didn't go anywhere, right? Specifically, the zeros of the function did not change. The zeros at x equals -2 and x equals 4 did not change. Now, let's take a look at why that is, all right? And it's kind of cool because you can really understand it from almost a purely formula perspective, right? The fact that f of x, don't worry about g or h, has zeros at x equals -2 and x equals 4, right, means the following. F of -2 is equal to 0, and f of 4 is equal to 0. So just for a moment, consider what g of -2 is, right? Just consider that, right? G of -2 is going to be 2 times f of -2, but f of -2 is 0, so g of -2 is twice 0, and it's still 0, right? Likewise, we could do it for -4, but let's actually not worry about that, right? If we think about h of -2, that's going to be 1/2 of f of -2, which is 1/2 times 0, and that's 0, right? So the plain fact is, when we multiply a function by a constant, all y values on that function get multiplied by that constant. But when we multiply a y value of equal to 0 by a constant, it still stays a y value of 0. It's that zero product law again, right? 0 times anything is 0. I mean, it's a zero product law in a slightly different way. So when we multiply an output of 0 by any constant, it continues to be 0. So what we're doing, right, is we're stretching or compressing these functions around the x-axis. We're literally making the distance twice as far away from the x-axis for the function g, and 1/2 the distance for the function h. But if we've got a function, right, or y values that are sitting right on the x-axis, then they don't go anywhere, right? They don't get stretched away at all, because they're sitting there right on the axis, and they have a y value of 0. So when we multiply that y value of 0 by 2 or by 1/2 or by 10 or by -22, it's still going to be a y value of 0. Excellent. So let's keep going. Vertical stretch and compress pattern. Let's take a look. Vertically stretching and compressing functions. The function h of x equals k times f of x represents a vertical stretch away from the x-axis of f of x by a factor of k if k is greater than 1. and a vertical compression of f of x towards the x-axis by a factor of k if k is between 0 and 1. Now, notice for a second, right? We are not allowing k to be negative here. We're basically saying, and this is very similar to kind of like exponential functions and their bases, we're saying, look, if what we multiply f of x by is a number greater than 1, then we're going to stretch the function away from the x-axis, right? The function's going to get kind of taller on both ends, if you will. On the other hand, if we multiply f of x by a number between 0 and 1, 1/2, 2/3, 3/4, something like that, then we're going to compress the function. We're going to like shorten it, make it closer to the x-axis. Let's take a look at more of this in exercise number 2. In the graph shown, g of x equals k times f of x. Letter A. Has f of x been stretched or compressed to produce the graph of g of x? All right, this should be simple enough. Pause the video now and answer that question. Well, it's been stretched, right? Because it's gotten farther away from the x-axis. Stretched because it has gotten farther from the x-axis. By the way, before we go on and answer B, notice just what we saw in the last part of the last problem. All of the x-intercepts, though, of f of x didn't go anywhere. They didn't go anywhere. Now, the second part of this, letter B, what is the value of k? Justify. Well, I want you to see if you can figure this out. And again, I'd like to point out that all this equation really says is that the y values on g are equal to k times the corresponding y values on f. Pause the video now and see if you can figure it out. Well, you can really use any 2 points that lie on f of x and g of x that have the same x value and that are kind of nice. So probably the easiest thing to do is look at this point and this point. So on f of x, right, specifically we know that f of 2 is equal to 3. We also know that g of 2 is equal to 9, right? And we know that g of 2 must be equal to k times f of 2. And since g of 2 is 9 and f of 2 is 3, then we're simply solving this equation. 9 is equal to k times 3. And therefore, it's pretty easy. If 3k is equal to 9, divide both sides by 3, and our k value is 3. That again works with any 2 nice points. You know, for example, right here, we have a y value of 2 and a y value of 6. So obviously, if we take a y value of 2 and we multiply it by 3, we get a y value of 6. So it doesn't really matter. The key is, right, you've got it to 2 different points that have the same x value because we're stretching kind of along a vertical line, right? It doesn't say g of x plus 1 equals k times f of x, right? The x's have to be the same to be able to think about that. All right, let's keep going. Combinations of transformations. Ooh, I like that. It's like alliteration. We can combine vertical stretches and compressions with shifting to make more complex transformations. Let's take a look at how that's done in exercise number 3. The graph of y equals f of x is shown below. Consider the function y equals g of x defined by g of x equals 2 times f of x minus 3. Letter A, what 2 transformations have occurred to the graph of f of x to produce the graph of g of x? Specify both the transformations and their order. All right, now the way I want you to think about this is if I literally tried to figure out what g of, I don't know, 3 was. If I tried to figure out what g of 3 was and I substituted it into this formula, 2 things will occur, right? That will help you think about what the transformations are and the order in which they happen. So pause the video now and see if you can figure them out. Well, literally, if I thought about g of 3, that would be 2 times f of 3, so I'd have to figure that out first, right? This is the first thing. And then I would subtract 3 off, and that would be the second thing. So the first thing that's happening is I'm taking f of x and I'm multiplying it by 2. And that is going to be a vertical stretch, right? A vertical stretch by a factor of 2. Now you could almost think about producing that graph, right? You could take this thing and this thing you could make twice as far below the x-axis, this one twice as far above, this one twice as far below, this one twice as far above, right? And then after you did that, you would take that function and you'd subtract 3 from it, which would take all the y values and make them go down by 3 units each. And what would that do? That would be a vertical shift down by 3 units. All right, that's it. Now, let's actually get to that graphing. Letter B. Show where each of the 4 marked points on the graph of f of x would be mapped under the transformations from A, and then produce a graph of g of x. So this is really cool. Let's actually do it. Let's take this point, and we'll go through the first one together, and then I'll have you do the other 3 on your own. The first point is at -7, -2, right? -7, -2. So let's talk about where that's going to go. Well, -7, -2, when I first stretch that away from the x-axis by a factor of 2, will go to -7, -4, right? All I'm doing is multiplying that y value by 2. Then when I shift it down by 3 units, -7, -4 will go to -7, -7. That's it, right? So the first thing I'm doing is taking my -2, multiplying it by 2, which gives me -4. Then I'm taking my -4 and I'm subtracting 3 units from it, and I'm getting to -7. Now, notice I'm not doing anything to the x value because neither one of these transformations has anything to do with horizontal motion. The first one is a vertical stretch by a factor of 2. The second one is a vertical shift downward by a factor of 3. Okay, now what I'd like you to do is also do that for that point, and that point. And then once you have those 4 points, plot them, and then go ahead, plot them and then flesh out what the function looks like. All right, let's take a look at the rest of them. We have got the point -4, 2. That'll go to the point -4, 4, and then that will become -4, 1. We then have the point 2, 0. That one's sort of interesting because the original transformation multiplying y by 2, it doesn't go anywhere. And then when I shift it down 3 units, it'll go to 2, -3. And finally, the last point, which is at 6, 6, right? Originally, when we dilate by a factor of 2, it'll become 6, 12. And then when we shift that, I'm going to move my little hand out of the way. When we shift that down 3, it'll go to 6, 9. Right? We can use those 4 points now, the points -7, -7, -4, 1, 2, -3, and 6, 9 to actually graph the following. And there is my graph of g of x. And of course, it looks very different now, right? If all we were doing was shifting it, then it would look exactly the same. It would just be down 3 units. In fact, if we dilated it, right, then it would have the same shape that we see in the blue. It just wouldn't have been shifted at all. It just would have been stretched. All right, let's do one last piece of this problem. Letter C. On the interval -7 less than or equal to x less than or equal to 6, for what values of x is g of x greater than or equal to f of x? How can you tell? All right, see if you can figure out and state an interval, right? A subinterval of this particular interval, for which g of x is greater than or equal to f of x. Pause the video now and take a look. Well, one thing that's kind of cool is you can almost like test it, right? So for example, let's say I took x equals -1. You know, is g of -1 greater than or equal to f of -1? Right? Well, here we are. Here's -1. And what I see is that g of -1, remember g is in blue, is -1, and f of -1 is 1. Is this true? And the answer is no, right? And the reason, of course, that it's not true isn't just because -1 isn't greater than or equal to 1. It's because at x equals -1, the red graph, which is f of x, is above the blue graph, which is g of x, right? This is getting into the how can you tell, right? G of x will be greater than or equal to f of x when the graph of g is at or above the graph of f. And that occurs for all values of x from here on. Now, I can't just say x is greater than or equal to 4. That won't work because that would imply it's also true at x equals 10. But what I can definitely say is it's true of all the values that's in here, right? So for all values from 4 to 6, this is true. How can we tell? Because the graph of g of x is above the graph, and I should really say at or above the graph of f of x. And we've talked about this before. We've looked at other scenarios where we've solved an inequality graphically, and that's exactly what we're doing here. Okay, let's take a look at one last problem. Exercise number 4. A factory has 5 identical 3D printers that print parts at a total rate given by the function f of t equals -7.5 t squared plus 90t, where t is the time in hours the 5 printers have been operational. The graph of f of t is shown below. A second function is defined by g of t equals 1/5 times f of t. So again, before we kind of like jump into everything, let's just make sure that we really understand what's going on here. You know, we've got these, you know, maybe a lab that's got 3D printers in it. They're printing away. And this graph gives us the total rate at which the 5 printers are printing. So, you know, we could say at 6 hours, let's say, they're printing at a total rate of 270, I think it's parts printed per hour, whatever they're printing, right? You know, at 6 hours, they're printing at a total rate of 270 parts per hour. Now, the first thing it asks us is very simple. Find a formula for g of t. And this really takes us right back to exercise number 1. Use the definition of g of t and the definition of f of t to come up with a formula for g of t. Pause the video now and go ahead and do that. All right, well, simple enough, right? We can now say that g of t, wow, that almost looked like a g. G of t equals 1/5 times -7.5 t squared plus 90t. Of course, multiplying by 1/5, which you can totally do on your calculator, is the same as dividing by 5. And so all of this, -7.5 divided by 5 is -1.5 t squared. And then 90 divided by 5 is 18. So the formula for g of t is -1.5 t squared plus 18t. Letter B. How could you interpret the meaning of the function g of t? All right, well, I want you to think about this for a second and really kind of go back and read the setup of the problem in order to try to interpret what g of t is actually telling us. Well, remember, f of t was the total rate of 5 identical 3D printers. G of t is 1/5 of f of t, so G of t is the rate of a single 3D printer, right? That's all. G of t is the rate of a single 3D printer. That's it, right? And it's important to be able to interpret, right, what functions are trying to tell us. All right, letter C. Sketch a graph of G of t on the same set of axes and label the point that represents its maximum. Verify on your calculator. All right, so here's what I'd like you to do. I'd like you to take your calculator out. I'd actually like you to put f of t in, or f of x in, as your first function. Set your window, right? 0 to, I guess it's around 12, and then 0 to 300. Make sure that you get that nice curve going in there for f of x. Then put in g of x, right, using this formula with x's instead of t's. Graph that, and also find its maximum point. Pause the video now and go ahead and do that. All right, well, if I put it into my calculator and I do as the problem asked, I end up getting something that looks like that. And notice yet again, the zeros, the x-intercepts of g of t, are exactly the same x-intercepts as f of t, right? Even though we've kind of compressed our function by a factor of 1/5, right? Every single point is 1/5 the distance it originally was from the x-axis. And in fact, if we then use our maximum command to find this point, what we end up finding is that it's at the point 6, 54. And 54 is 1/5 of 270. Notice again, right, that the x-coordinate of the turning point, that didn't change at all, right? You know, we want to think about these vertical stretches and compressions, in this case it's a compression, right, as being like, if I go to a particular point, like 6, 270, the corresponding point will be at 6, 1/5 of 270, which is 54. So the peak rate at which one printer can print is 54 parts per hour. All right, let's wrap this up. One thing I love about vertical stretching and compressing functions is it works a lot like vertical shifting, not horizontal. We'll get into that in the next lesson, but the vertical stuff. You're literally taking a function and you're multiplying it by a number. You're taking all the outputs and you're multiplying them by, let's say, 4. And that means every y value is going to be 4 times the distance from the x-axis that the original y values were. Or we take every y value and we multiply by 1/2, meaning that they're all going to be only half the distance they were away from the x-axis. Now this is very important because oftentimes we might have a parent function, right? And we want to have exactly the same x-intercepts in a new function, but we want, let's say, the new function to be either closer or farther away from the x-axis by a certain factor, twice as far, half as far, what have you. And we do that by simply multiplying the whole function by some positive number. If that positive number is greater than 1, we're stretching it away from the axis. If that number is between 0 and 1, we're compressing it towards the x-axis. All right, well, obviously, since this entire unit is on transformations, we're going to see this more, but we're going to definitely see vertical stretching and compressing throughout the rest of this course. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.